Hi everyone, my name is Timothy Fox and I'm here to talk to you about an exciting new framework called BigDL. BigDL allows us to do distributed deep learning. Now, I've been working on developing and implementing big data applications on the Hadoop platform for years. One of my interests in big data is how to use this data for doing machine learning at scale. Early libraries like Mahout and others attempted to do this. At the same time, I've been interested in deep learning. Earlier in my career, I used deep learning models for such diverse tasks as finding oil and gas and understanding natural language. I'm excited about BigDL because it brings together two of my personal passions, massively distributed processing on big data and deep learning. First, let's talk a bit about big data. Now, as you may know, there is a tidal wave of data happening today. As a matter of fact, while structured data has been growing linearly, we can see that big data drivers such as smartphones, wearables, and other things, etc., have been leading to a growth of unstructured data that is growing at even more quick rates, exponential rates, in fact. Now, Gartner came up with the 3 V's of big data, and most of you are probably familiar with those: volume, variety, and velocity. And those still accurately describe the challenges that we have in big data today. Now, Google started things off by publishing a couple of white papers that fundamentally changed the way we look at big data sets. These were Google File System, known as GFS, and MapReduce. Now, Google File System talked about storing immutable, append-only data broken up into large block sizes which were replicated on clusters of machines. MapReduce talked about a framework which would allow us to do parallel processing on that same cluster. The big idea was this: we can have compute nodes and our data nodes running on the same boxes, one and the same. Now, Doug Cutting from Yahoo implemented these ideas in an open source framework that we now call Hadoop. And it is this open source framework that became the basis for most of the big data ecosystem today. Before there was Hadoop, storage and computing were basically separate functions that usually ran on separate machines. Now, this works great for HPC or high performance computing, doesn't scale very well to big data. Now, Hadoop merged the two. So Hadoop's high data resiliency through HDFS and its flexible cluster computing framework known as Yarn has given birth to a new generation of processing tools, one of which is called Apache Spark. Apache Spark allows us to do processing that is both faster and more flexible than the classic Hadoop MapReduce. It does this by making use of in-memory data processing. And while Apache Spark can run with or without Hadoop, it is combined with Hadoop that Spark is able to process very large data sizes. Now, what is machine learning? So, machine learning is basically an algorithm that learns from data. That means it gets better at accomplishing its tasks by getting more data. Now, ordinary programming algorithms simply follow the instructions that are given to process data. Little data or more data, these algorithms will do the same. Not so with machine learning. Now, there are some excellent machine learning libraries that are out there that many of you are probably familiar with. In Python, we have scikit-learn, which is a very powerful library which allows us to do machine learning. And in R language, there are many packages that are part of the CRAN repository that can do the same. Now, the problem is that most of these libraries are not parallelized. So they're good for single machine architectures, but they're not suitable for scaling horizontally, and particularly not on Hadoop big data. Now, libraries like Mahout were early attempts to bring machine learning to data of massive scale. But, and this also featured entirely parallelizable algorithms. Attention was focused on parallelized versions of common machine learning algorithms. The problem is that these original processing framework MapReduce is not well suited for the iterative nature of most machine learning problems. Spark attempted to solve this by superior execution model and greatly improved in-memory processing capabilities. Now, deep learning simply means running with neural networks on more than one hidden layer. These are modeled loosely after the human brain and are excellent at trying to recognize patterns and sensory data. So these were popular in the 1980s, fell out of favor in the 90s and 2000s as statistical methods yielded better results. Now, neural networks are a very powerful tool, but only recently have modern computers been up to the challenge. Early neural networks did not scale for the following reasons. First of all, compute power was insufficient for the time. Training datasets were also insufficiently sized for good results. Initial weights were not set in a way to achieve quick convergence, and we lack the ability to parallelize our work. So what we've seen, though, is now we finally come to the point where deep learning is poised to revolutionize the way we process data. Now, one of the initial barriers to deep learning was the thought that neural networks are not very parallelizable. While we might be able to deploy a trained neural network at scale on our Hadoop data, certainly training networks at scale and very large data sizes is difficult. Now, companies like Google prove these assumptions incorrect. Google has successfully translated many deep learning models with massive training sizes. The results, like Google Translate, Google's Word2Vec, and others, are the results of that efforts. Still, Google has some advantages that you and I do not. While Google has open sourced some parts of its workflow, other parts such as TensorFlow and Kubernetes, which when running at massive scale, particularly by training, is no easy feat. Okay, so here you can see some of the frameworks that we have now in deep learning. The best of these usually have a powerful sponsor. Google has TensorFlow, Amazon has MXNet, Microsoft has the Cognitive Toolkit, Facebook has Caffe2, etc. There are even excellent high-level frameworks like Keras, who can use some of these as a backend. We love and use all of these tools, and by no means disparage any of them. Now, back in 1968, there was a guy named Gordon F. Hughes who published a paper called On the Mean Accuracy of Statistical Pattern Recognizers. Now, Hughes described a problem which we now call the Hughes phenomenon, which described that as we deal with data with large numbers of dimensions, the amount of training data that we need to accurately infer pattern increases rapidly. Basically, what that means is that if we're going to look at more than just a few columns in our data set, then we need to train on a lot of data. This is one meaning of the term curse of dimensionality, and this is one reason why early neural networks didn't scale well beyond toy problems. Now, this flies a little bit in the face of the conventional wisdom of applied statistics, was that we're best off training with a good, reasonably sized statistical sample of our data set. So according to Hughes, I need a lot of data in order to train my models effectively if I'm going to have more than a few dimensions. And as a big data practitioner myself, that insight warms my heart. Now, here's the problem. Unless you are Google, Amazon, Facebook, etc., you might have a tough time pulling this off at scale, even if you have the machines to do it. That's because most of the deep learning frameworks are either not parallelizable or they lack key infrastructure pieces to run on very large dataset sizes. Now, one option is we can use cloud offerings, for example, using Google's Cloud ML framework. However, Cloud ML is not open source, and so that isn't something we can replicate easily outside of Google infrastructure. Okay, so what about GPUs? Well, that's a great question. So GPU processing is one of the great leaps forward in recent years when it comes to deep learning. Now, using GPUs will allow us to do things 10 times faster than traditional CPUs, and by having multiple GPUs in our box, we can create a super box that can power through our training up to 100 times faster than a CPU alone would. Now, here's the problem. GPUs, while very powerful, are difficult to parallelize in large clusters. Most work on GPU processing tends to be done on a few machines with large numbers of GPUs. Now that's great if we're trying to parallelize our compute. So for Bitcoin miners and other similar problems that are almost entirely compute bound, then scaling with large numbers of GPUs is great. But if you think of this, this is a lot like an HPC architecture we call big compute, one in which we're doing lots of number crunching on small to medium-sized data sets. That's fine if that's what we're doing. But in deep learning, we have a problem that is both big compute and big data. That means we're going to have to find a way to scale just beyond a handful of nodes, no matter how many GPUs we might have. Now, fortunately, recent Intel Xeon CPUs have vectorized linear algebra compute capability that rival that of GPUs. This is done through Intel's math kernel library, which provides vectorized implementations of linear algebra, fast Fourier transforms, vector statistics and deep data fitting, vectorized math and optimization, and most importantly for us, deep learning. Well, we may be able to get more raw performance out of a GPU. CPU-based processing does have one advantage that a GPU does not: the ability to quickly and efficiently process the I/O required to scale to huge data sets on clusters of up to 1,000 machines. Now, it's not that GPUs are bad. We love GPUs, and we consider them a great step forward in processing deep learning libraries in some context. I'm just arguing that, however, in big data scenarios where we're looking at massive parallelization, we also need to look at the ability to parallelize our I/O and not just our compute. And modern Xeon processors give us this sweet spot between fast vectorized compute capability and scalable I/O for big data. Okay, let's introduce BigDL. Now, despite the embarrassment of riches that we have in excellent deep learning libraries like TensorFlow, Caffe, Theano, MXNet, and others, one thing that's been missing so far is the ability to take all of that deep learning goodness and bring it to the world of Hadoop and big data. That is, until now. BigDL is a new framework from Intel that allows us to parallelize our deep learning training and deployment to our Hadoop and Spark clusters. It's an exciting way for us to solve this age-old problems of how do we take deep learning to a problem that is both big compute and big data, and to do that at scale. Now, I'll say one thing for Intel. They know their CPUs well, and they know how to squeeze the most performance out of them. And they're able to take that knowledge and apply that to making the fastest CPU-based vectorized processing available. Remember, the goal here isn't try to outcompute a GPU on a single node. The goal is to develop a system that combines vectorized compute capability and parallelized I/O for scaling to petabytes of Hadoop data. Now, BigDL gives us both massive compute and big data. It allows us to balance our needs as well as allowing us to run with massive scalability. Now, are we saying that we don't like TensorFlow, Caffe, and other deep learning libraries? No. We love and use TensorFlow, Caffe, Keras, etc. What I am saying is that BigDL is the best way to scale our deep learning models to our large-scale big data ecosystem. All right, let's compare, though, BigDL versus TensorFlow. So, in the framework, now TensorFlow provides us a C++ engine with a Python backend. BigDL gives us a Scala engine with a Python backend. Now, acceleration, again, as we talked about, BigDL is using primarily vectorized CPU-based optimization, while TensorFlow is giving us mainly GPU-based optimization. Now, Hadoop data, BigDL allows us to run natively on Hadoop data, whereas TensorFlow accesses Hadoop data as a client only. In distributed operations, BigDL is going to rely on Spark for massive scale, while TensorFlow out of the box does not support massive distribution. Both BigDL and TensorFlow allow us to run TensorFlow models. And so, in summary, we can say that while TensorFlow is an excellent library for small-scale data, when parallel processing is not a main concern, BigDL is excellent for distributing deep learning models to massive scale on big data. So, BigDL is going to give us both big compute plus big data. It helps us in balancing our needs between big compute, giving us fast linear algebra, Intel MKL library, and big data I/O parallelized to run on many CPUs. It gives us massive scalability. It allows us to run on Hadoop and on Apache Spark. Now, BigDL also integrates with the BigDL ecosystem. It allows us to import our TensorFlow and Caffe models and use them at scale. What's more, high-level libraries like Keras can use BigDL as a backend. That means we can take our Keras code and run on whatever backend we're using and easily port that to run on top of BigDL. Okay, so here's how we can install BigDL. First, we need a Hadoop cluster. And so that means is that we can use Cloudera, Hortonworks, or MapR, or some other distribution. Now, we can also use cloud-based versions like Microsoft's HD Insights, Amazon's Elastic MapReduce, or EMR, or Google Dataproc. Then, we need to ensure that we're running Apache Spark. Most of the Hadoop versions also include an optional support to install Apache Spark as part of their install. We also need to have a Python distribution available. Many developers prefer Anaconda for this. We can also use the system Python. Finally, we need to set up and install BigDL itself. Well, does this sound daunting? Well, rest assured, we're making this easy for you. So, the BigDL sandbox. So we have a Docker container that is going to make running BigDL easily. This Docker container allows you to download and install BigDL in one easy step. This isn't for production use, but it will help you in getting going right away and playing with BigDL. And one advantage of our Docker container is it's open source and transparent. So the Docker file is available as part of distribution, and you can modify and our sandbox to meet your needs and distribute it at will. Now, if you haven't heard of it, Docker is a revolutionary way to package applications, which allows us to package an application together with all of its dependencies in one reusable module that we can run on any platform. So to do this, we need to download Docker for our platform. So Docker has versions for Windows, Mac, and Linux. If you're running Windows, we recommend using Docker for Windows, but you'll need Windows 10 Professional for that with Hyper-V installed. Otherwise, you're going to have to fall back to Docker Toolbox. Mac and Linux versions have Docker for their platforms as well, which should be able to effectively run on modern Mac and Linux systems. Okay, so let me demonstrate how we can download Docker. So we'll go here to docker.com, and we can find the version of Docker for our container. And we will get Docker. I'm running a Mac, so I would click on Docker for Mac. However, if you're running Windows or Linux, you can get a download for your platform. So once we've downloaded and installed Docker, we should have Docker then available. And as you can see here on my Mac, I have Docker running now. So once we have Docker up and going, we can then go and install and download the Docker tutorials from Intel. So to do this, we're going to go to github.com, and it's temporarily available on Elephant Scale. That may change here in the future, / BigDL tutorials. And what we're going to do is we're going to go ahead and either clone or download this for our platform. The easiest way will probably be for us to just download the zip file to our computer, and then we can go in and install that as well. Okay, so once we have that cloned or downloaded, we can then go and we can go to the BigDL tutorials directory that I have, that I've now had. So we have a script that we can run here that will run our BigDL in the Docker container all in one step. So on Mac and Linux, we can run that from the command line by simply saying run BigDL container.sh. And then we're going to run that with the container name, which should be available from Docker Hub at Intel/BigDL. Okay, we're going to go ahead and run this. Now, if you choose to do your own build of our Docker container, which we highly encourage you to do, you would substitute Intel BigDL with the image name of your custom build. So, and you can do that simply by going in and compiling that. But in this case, we're just going to run Intel BigDL. Okay. So you see now we are running here, and this automatically will start up Jupyter Notebook running on our computer. So now this is running inside the Docker container, but the advantage of this approach is that we are able to do this here and load this directly in our browser on our computer. So let me go ahead and start this up. And you can see here I copied here. Now our work is going to be right here under work. So now this work directory is going to be mapped to your local file system. So that means any notebooks or other things that we want to load on the Docker container, you can do it after local files. So this is kind of the best of both worlds, because we're doing all of our processing for BigDL inside the Docker container, which will help us especially on running on non-Linux platforms that may not have Hadoop or Spark running. However, it also means that we can load all of our local data on our own computer. So any notebooks or other data or intermediate data or results that we want to save, we have the ability to load that even outside the Docker container. Let us now go and check out what we have. So we have here a BigDL distribution. We have some data. We have our Docker files. We have some images here. And we also have some Jupyter notebooks. So since we're running inside of Jupyter, I am going to go and click here on the notebooks directory. And we just want to make sure right now on where we are in running our Docker containers. In the next video, I'm going to go over actually running some examples and tutorials of how to use Docker for big learning. But for now, I'm simply going to load up this testing123.ipython notebook. And I also suggest, if you're following along with me, to please go ahead and start that up on your own machines as well. Again, you should be able to run this on any platform, and that's the beauty of running with the sandbox within Docker. So let's go, and I'm going to go ahead and click on testing123.ipython notebook. So here, you can see here, this is going to help us to test our BigDL installation to make sure everything's running properly. Now remember, BigDL has a lot of moving parts. We have Hadoop, we have Spark, we have BigDL itself, and we have Anaconda Python, and all of these things running together. So we need to make sure that this is all working. So one of the things that running along with Spark is going to give us is a couple of instantiated objects, namely the Spark context and the Spark session. The Spark context applicable for versions of Spark before 2.0, and Spark session being included there. So you can see here that we do have the SC object here, the newer API here. Also, we see that this is available as well. So these are both available, and we can see this here on our installation. Okay, so let's now test creating a data frame in Spark. So I'm going to go ahead and run the Spark. Now notice that this is a Spark data frame, so we're going to require Spark running to actually make this work. And you can see that we're running this, and we should be getting our results shortly. There we go. So you can see here we just create a Spark data frame. Now notice this is different than a Pandas data frame. This is a data frame that is distributed to our cluster. Of course, we're running this inside of a Docker container, which means, of course, that we're only running on a single node, but nevertheless, we have this ability to be distributed on a Spark cluster. Okay, so now we're going to be getting into importing data from BigDL. And what we're going to do is we're going to do our imports here in Python, making sure that our imports are looking good. So let's go ahead and run this cell. All right, so we ran this. We tried to do our imports of BigDL, and then, as it says here, our imports are looking good. Now we're going to be doing a hello world here in BigDL. So what we're going to do is we're going to initialize the engine here, and we're going to show the version of BigDL that we're running here. And we're going to go ahead and try to create a linear layer in BigDL just to make sure that this is all working. Okay, so you notice we said hello BigDL world. We're getting our BigDL version here, and now we are running a create linear as well. So looking good. Now what we're going to do is we're going to ensure that we have our Python environment running well. So I'm going to be testing our ability to run with NumPy and Pandas here. So what I'm going to do is I'm going to create a NumPy array, and I'm going to be setting up a Pandas data frame. And you can see that there we go. There's our data frame. All looks good. Now note here, of course, that we are running as part of the Python environment. And so one of the advantages of that is we get the richness of the Python ecosystem. Some of our examples that we're going to do later actually involve running with NLTK. So we're going to import NLTK here. And we're going to go ahead and run this as well. So to do that, we actually need to install NL2K. No problem. We can do that. So what we're going to do is we're going to say which pip3, and I'm going to just say pip3 install NLTK. Okay. And actually, to do this, I'm going to need to do this, run this from within the Docker container. So in order to do that, I'm going to need to do that within the Docker container. So let's also do some graphs. So we will go ahead and run some graphs here so you can see the graphs that we have running. And we're also going to ensure that we have the Seaborn library running as well. So if you see this nice distribution plot, then we're good. So if we're all here, everything ran well, then great. We are ready to explore BigDL. Okay, so now we've successfully installed BigDL. We've ran through an example notebook that while we didn't do much with BigDL, we've nonetheless tested our configuration and made sure that all is running properly. So now we're going to be going on in the next video and doing our first simple deep learning models in which we use BigDL for doing some actual deep learning. So I look forward to seeing you in the next video. Thank you so much.